In this video tutorial, we'll look at linear and nonlinear buckling analysis of a slender column. So we'll this time use ANSYS Workbench, and this is our project schematic, and from our toolbox we'll start by creating a static structural analysis. The engineering data is simply the material information, and in our case by default we'll use a structural steel, and the Young's modulus of that is 200 gigapascals, and Poisson ratio 0.3 by default. So in the project we can define our geometry based on design modeler. In design modeler we simply need to create a line as a line body, and we'll mesh that with a cross section representative of a beam element. The first thing we do is to generate a point, so that can be done under create point. We can create a point from coordinate files, or also by seconds of delta, seconds of n, or from manual input. So in this case we'll just use the manual input, and we'll make the point at 0, 0, 0, and click on generate to create that point, and we'll add another one, and again it'll be from manual input, and this time we'll create it in y direction 1 meters. So generate that. So we have two key points here, or 2 points in workbench terminology, and we'll need to define a line body between these points. So we can create a concept line from points, and we can pick these 2 points and press Ctrl for the second one, and then apply, and that will add material to create a line body, and generate that as well. So now we got a line body, and we haven't got a cross section selected yet, so we need to define that cross section as well, and that will be done under concept cross section, and we'll try a simple rectangular cross section. And from the details view of that cross section we can make B 0.01 meters and H 0.02 meters. So that will be 10 by 20 millimeters in the cross section. That line body, we can go and specify that should use rectangle 1, and again checking the rectangular cross section 10 by 20 millimeters, and you can zoom in the view. That is where the beam or the column is going to be created. So that is effectively all we need in terms of geometry from design modeler. We can exit design modeler or simply save our project, and once the model is saved we can then right click on model and start ANSYS Mechanical. So ANSYS Mechanical generates this as a geometry that has been transferred from design modeler. So we can see that under geometry line body, and the cross section is also moved to mechanical, and the mesh isn't there yet, so that's what we need to create next. So we can specify a mesh control, a sizing, and we can do that based on a line. So we can select this filter for an edge and then select this line and then click on geometry and apply. And we can specify either the element size or number of divisions. So let's go for number of divisions of 10. So press enter. So this line will in fact be created in terms of beam 188 elements in the background. So Workbench will be running ANSYS Mechanical at the background using the beam 188 elements. So we have defined the line division, but we haven't meshed it yet, so we have to generate the mesh. So click on update. So that creates our mesh for these elements, and we can see that it is created in a correct rectangular format. And next structure input is the loads and supports. So we know that it's got a fixed support at the base, so I need to select that point by selecting the first filter for the vertex and select this vertex, apply on the geometry, and that selects that point as a fully fixed point. And the other one I need to apply there is a single force at the top. So load, force, and again I need to select a point at the top and click on apply. And I can define the force on this based on components. So I need to do that as -1 newtons, and that is in the y direction. So the force is specified, and as an output I also want from this the total deformations and the total stresses. But since these are beam elements, you can't see the stresses here, but you need to use the beam tool. So if you go to tools, beam tool, you can specify that you want direct stress, minimum and maximum combined stresses, etc. So if I solve this now, I can see that the stresses and deformation is calculated under solution. So the total deformation, and this is in terms of meters, and it's a very small amount, of course, because it's just a unit load applied, and the direct stress is 5,000 pascals. So that is exactly what I was getting in the mechanical APDL as well. The mechanical solution in Workbench typically creates an input file which runs using mechanical APDL in the background, and the results are then written back in and displayed for the user. So this is our structural model completed, which is just a static analysis, and it's all linear elastic, and we are getting stresses, etc., all accurately on this. So I'm happy to progress to eigenvalue buckling analysis on my project schematic. So if I drop that on the solution, that will transfer the engineering data, geometry, model, and pre-stress solutions to my eigenvalue buckling analysis. So when I go to mechanical now, I can do a refresh of all data, and I can see that eigenvalue buckling is also shown on my outline tree. So pre-stress is defined, analysis settings are defined, and by default it's looking for 2 modes. And on the solution, what I can do is add total deformation, and that's going to be for mode 1 of the buckling, and another total deformation, and I can change that to mode 2 of buckling. So if I do the solution now, that will solve the buckling analysis. So buckling analysis has completed, and I can look at the total deformation for the first one, and I can read from the graph the multiplier is shown as 822. That is exactly what I got as my first buckling mode load factor in mechanical APDL as well. In the second buckling mode, I'm getting 3289, and that's again the same as the previous mechanical APDL analysis result. So that is a straightforward static analysis linked to an eigenvalue buckling analysis in Workbench. The next thing we can do with Workbench is to create in our project another linked static analysis that would create a nonlinear analysis. So we can then open the model again. We can go to mechanical in Workbench, and we can see that static structural 2 is now appearing on the tree, and we have the analysis settings, and by default number of steps is 1. That's the current step number, and the step end time. What we have done in the previous mechanical APDL run was to change that step end time to 1000 and turn automatic time stepping on, and we can control it by time or number of sub-steps. So let's say time, initial time step, let's say 5 seconds, minimum 1 second, and maximum 10 seconds, and enter that, and we can specify some set of loads again for the structural analysis. We need to specify again our support, let's say fixed bottom fully, and let's apply a force at the top. So that load is going to be a force, and selecting this point, apply for the geometry, and then define by components. So it's going to be minus 1000 newtons, and that is going to be ramped from 0 to 1000. Now, of course, we have seen that the buckling will happen around 822 newtons, but it should be able to carry some more load because we have simply assumed a linear elastic material. But in order to start the buckling process, we need to apply either an updated geometry or a perturbation, maybe a force. So this is something we can do here as a simple force again on that point, apply, and define as a component in the x direction this time, let's say 1 newtons. So that will try to push the beam in the x direction to perturb it. So that is really all we need to solve this, and in the solution we want to see the deformations and also stresses. Again, the stresses, the usual stresses don't apply to beam elements. We need to use the beam tool. So create the beam tool, and under the beam tool we can approach the direct stress and combined minimum and maximum stresses. Under the analysis settings, we also need to make sure that large deflection effects are turned on so that we can see the nonlinear effects of this, and we need to solve this again, and we can look at the solution information and see force convergence or other information that's relevant to our problem. So this has solved and converged to a solution even at 1000 seconds. We can look at the total deformation and animate that. We can see that around 800 seconds, which is corresponding to 800 newtons, our model is effectively buckling. So we can stop that, and we can also look at combined stresses or direct stresses, and at the end of the load step again we are getting very large stresses, just because the deformations are very large. And just past 847 we can see that the stresses are getting very large, because this is a typically nonlinear analysis and we have assumed elastic material properties. So we can animate these again, even in a refined way, for 10 seconds and 100 frames. So we can see that the stresses are increasing, and as the stress approaches the buckling values, it starts to buckle. So this is a quick demonstration of how you can do a static analysis, which is followed by an eigenvalue buckling analysis, and we can then progress to a static structural analysis, but this time using nonlinear geometry effects. In the last section of this demonstration, I have added a commands snippet into the nonlinear static analysis. So if you go to static structural and click on the insert commands toolbar button, this will put in a commands snippet, effectively a simple text document where you can type in APDL commands. So we can say where this should be run. It will be an object within the tree, and it is going to target mechanical APDL, and what we are doing here is issuing the upgeom command. So the scale is 0.01 and it's going to read the eigenvalue buckling analysis from this location, and the file is file.rst. So the location you can confirm from the analysis settings of the eigenbuckling. So under the analysis data management, I can see that solver file directory is specified here, so I can copy that and then copy that into my command snippet as I require. It is worthwhile checking using the Windows File Explorer to see that that file exists and the name of the file is indeed file, and the extension will be typically RST for the results files. So with this in the space, we can solve this time by updating the geometry and creating our shape imperfection. And force, which was used to perturb the model, is suppressed, so simply use suppression to remove this from the model, and commands snippet will update the geometry and create the shape imperfection instead. And in the solution everything else is the same, and when we run this we'll get a typical simulation that will show that at the beginning the load is carried fine, and as you approach the critical load the model starts to deform and then buckle. And we can look at deformations or stresses at any point in the model. So this completes our buckling tutorial.